Over the past 2 years, I extensively tested the PSI Audio AVAA C214 in 10 different studios to figure out if they work, how they work, and to finally answer the question if they are worth your hard-earned money. The PSI AVAA is the only commercially available, fully automatic, active bass absorber in the world today. A technology so unique, they actually had to invent their own sensor just to measure it because nothing existed that could. And if you want to watch the main review, I'll link it in the card right now, and you can also find it in the description. But today I'm going to sit down with the man who actually built it. And he's going to explain how the technology works, why prototypes kept failing even when the theory was perfect, and what the future holds in terms of products. Hey, what's up? It's Jesko from AcousticsInsider.com, where I teach home studio acoustic treatment techniques for audio professionals, but without all the voodoo. 2 quick notes before we get started. Unfortunately, the audio on Yvan's end wasn't great for the first few minutes, so I've added subtitles until we got that fixed. But it does get fixed, and I think you should stick with it because the conversation is absolutely worth it. Second, if you are interested in picking up an AVAA or 2 after watching this, I've included a link in the description. Buying through that link supports me and everything I do at Acoustics Insider at no extra cost to you. It's one of the best ways to support the channel if this technology is interesting to you. All right, that out of the way, my guest today is Yvan Becher, the R&D manager at PSI Audio. He was hired specifically for the purpose of developing the digital version, the C214, of the AVAA active bass trap technology. And this is the first time Yvan has walked through the full development of the product on a channel like this. So in this conversation, you'll learn how the AVAA creates a virtual hole in the wall and why it's not noise cancelling. We'll also get into how they had to design their own reverberant chamber just for testing and hunt down studios that had 15 hertz room modes. We then get into the one skill from speaker design that actually made this whole thing possible and what's coming next, including products that don't exist yet. Let's get into it. Yvan, great to meet you. Thanks for making the time. Can you just start out by telling us a bit about who you are, since when have you been working at PSI, and what is your role at PSI, and in particular, the AVAAs?
Yeah, nice meeting you too. So my name is Yvan, as you said it, and I work at PSI as an R&D manager. And my role is mainly focusing on the AVAA. I was a developer, an engineer, also for the tests and everything. And actually, I was hired in the company 6.5 years ago, approximately, to develop the AVAA C214. The AVAA is a big product or a big part of the market of PSI. And the idea is that with the analog version, like we were doing it traditionally with the analog components soldered by hand, produced with wood cabinets and everything, it was difficult to increase the size of the production. So the idea to develop a digital solution and also a more industrial solution with the C214 is really to be able to go a step further.
Okay, so it's as much kind of an industrial reasoning as it is kind of just product development. The original analog version was just a bit difficult to scale at the same rate, basically.
Exactly, and as you know it, in analog, you are stuck at the version that you are soldering on the PCB, more or less. But with the digital in low frequency, it's not that critical because, of course, you take more time to make the calculations and everything, but in low frequency, you got the time to do it. So the idea was to have a DSP to be able to keep the possibility to update the device.
Yeah, sure. Okay, amazing. Because I mean, it's worth saying at least once, this is a very unique technology. It's a one-off for the moment, at least. Fingers crossed.
Yeah. Fingers crossed, exactly.
Fingers crossed. It's a one-off for them at the moment in the acoustic treatment industry, in the acoustic treatment world. It's definitely something that I haven't seen anybody else try even. And so it's a remarkable technology. So mad props to everybody involved. It's very unique. I'm very impressed. I think everybody is, I guess, who uses them. And obviously, and I mentioned this in our email exchange, obviously my slogan is the without all the voodoo. And I can testify this product, this technology definitely has no voodoo involved. It is pure science. I think it's hard to explain really how it works, but maybe you can give it a go, especially if we're talking to somebody who isn't really an acoustics expert. And yeah, what would you say? What's the easiest way to explain how this actually works?
That's the tricky question, as always. But basically, it works like a passive resonator or a passive absorber, except that we have a microphone in front of the device and we are driving transducer. So it allows us, with the energy of the amplifier, to have a bigger object than its real size. So instead of having a handballed resonator or like you have in your studio behind you, big passive bass traps, you can have a smaller object doing exactly the same because you have energy inside of the device. If you want, it's really like opening a window. So instead of opening a window the size of the window, which is or like the bass trap you have behind you, you have a window which is much bigger than the real size of the object.
Yeah, so you call it an active velocity acoustic absorber, but it's not noise canceling. That's a really important difference, right? This isn't anti-sound in very simple words.
Yeah, exactly. So as you said it's really active velocity. So what we are doing is that we have a microphone in the front which sends pressure, but we transform this pressure into a velocity with the transducers. And this allows us to act on the acoustic impedance because the impedance is pressure over velocity. If you measure the pressure and you control the velocity, then you are imposing the impedance. And we impose an impedance which is lower than the air. And this leads to the absorber, which is bigger than its real size. Because if you do the impedance of the air, then you just have the size of the object. But if you go lower, then it's like increasing the size of the object. Noise cancelling in the terms of you are not sensing the pressure and just counter the force. You have a specific transfer function, I would say, between the microphone and the transducer, and that's the secret sauce where the magic happens.
Yeah, of course. And that's really important that stays proprietary with PSI because that's where the money is in the end. Obviously, you design this, or the product is designed as a bass trap. I think it's supposed to work between 15 hertz and 150 or that some range like that. Is that correct?
Exactly. Yeah.
I'm personally just curious what variables determine which frequency range it actually works at. Like, let's say you wanted to make this work up to, I don't know, 500 hertz. Is that even possible? And what would that mean?
That's a good question. Actually, to 500 hertz, we know that it works in the tube, but not in the 3 dimensions. We are working on it, but it's kind of very difficult because the limitations are in the distance between the transducer and the microphones.
Because of wavelength, I assume.
Yeah, exactly. And as soon as you have high frequency in the equation, then you have less time. So delay becomes critical. So at 150, you have plenty of time to do the calculation and have it to absorb even at 150. But at 500, you have to increase the speed of the processor and everything. So it's more like technical limitation. But at least you can solve them now because you have processor that can handle it. But then you have physical size of the object. So you have a transducer and you have to place the microphone, not in the front, not next to it, not too close, not too far. And that's a bit of the research that we are doing now.
Talk to me a bit about what it is like working on this, or what it was like developing the new digital version. For you personally, I'm sure there are lots of ups and downs, because I know when you're developing something new, You're working on something and you try something, it doesn't work. You try again, it doesn't work. You try again, it doesn't work. And at some point, you've got something and you're like, now I know this is going to work.
Yeah, basically the AVAA story is really this. One day you're happy and you're smiling and you're like, okay, today I'm on something. I will revolution the acoustics and everything. And the day after, you go in another room and you measure something and you're just lost because you don't understand what's happening. So you're just down like crazy. So you keep pushing because in the AVAA story, you get the theory, and in theory, everything works. And then you go to the prototype and you test and everything should work, but nothing works.
Nothing works.
and,
Oh my God,
and you just get back to the theory and you say, okay, what are we missing? And absolutely nothing. So you get back to the prototype and it's like an empirical work with the AVAA. It's really like, if you have an idea, then try it. And it's really faster than going through the theory simulations and everything.
Yeah.
That's a bit of the story.
Sounds very much like, on one hand, because you're working at kind of the edge of science to some degree, not just with the technology itself, but then also the how complicated sound fields in real rooms are, right? I think that's one of the things that people underestimate, just how complicated acoustics in small rooms is if you actually try to fully understand it, which barely anybody does, no matter how much they claim they know, because it is just so incredibly complicated.
Exactly. In the low frequency, you can do some hypothesis. Sometimes it's right, sometimes it's wrong. And so when it's right, then it works. If it's wrong, it doesn't work. And you really have to find the balance between where the hypothesis is right, and then you switch to another context. And that's what's defined, the low frequency in the small rooms.
I think that's a perfect transition to the question that I had about testing the unit. How did you, obviously you can stick it in a real room and then do some measurements. And like you say, then let's say 60-70% of the time it works, 30% of the time it doesn't work. But is there a systematic testing procedure in place? And what does that even look like?
Yeah, so at the beginning, we didn't know how to measure the active absorber because we were the first one to develop it. So we are thinking, okay, we will go to the guy that is manufacturing the foam or the wool. And actually it works for the high frequency, but in low frequency, it doesn't work anymore. So we were like, okay, we have to find a way to measure that. So first prototype, what I remind with the C20, so the analog version, is that we were inserting a microphone inside of the AVAA, so in the closed cabinet, to see if the pressure was right and proportional to the velocity and everything. But this was kind of weird because it took us like 20 minutes to calibrate the unit, or even 30 minutes to calibrate one unit. So it was taking too much time. So second step was to develop our own sensors. And basically this is an acoustic impedance sensor. So we combined an electret microphone with a Ray-Ban microphone.
Okay.
The Ray-Ban microphone is basically a velocity sensor. So by combining these two, we were able to measure the acoustic impedance in front of the device.
Impressive.
And that's how we calibrate them. And then we try to reproduce the same transfer function. So it's like really reproducing the same schematic all the time.
Gotcha.
We don't need this sensor anymore. And once you're ready with the calibration and the measurement of the device, then you go in the room.
Okay, I was just going to ask.
You don't know how to measure.
Because I was just going to ask, does the room that you do this in matter at that point yet? Or do you need to do this in an anechoic chamber?
So at the beginning, we went in the anechoic chamber because that's what we know, and we are calibrating the monitors inside. So we were like, okay, go into the anechoic chamber. And then we were like, okay, but we have to build reverberant chamber as well,
Yeah.
because we want to measure the room modes. So we built a reverberant chamber which has a 60, 80, and 100 hertz room mode.
Okay.
And that's a bit of a first validation.
Yeah.
So, and this validation is just done by you place a microphone in the corner, the opposite corner of the absorber, and you see if you have a decrease in the pressure and a decrease in the time decay of the room. So basically, we were computing the RT60, the Q factor of the room modes and everything.
Right.
So that was the first step.
So that was down
And then
to
we went.
That was down to 60 hertz. So how do you do down to 15 hertz?
Exactly. So it was only down to 60 in our chamber. And then we said, okay, now if we want to see that it works at 15, we have to find the mode at 15. So we went in the studios where there was a mode at 15. And then we validated in several studios to ensure that it works at 15 as well.
Right. Okay, that makes sense. Because that means a big studio, first of all. You need a big room. But then the only way to really do that was to actually iteratively test it in multiple rooms and
Exactly.
kind of get a confirmation through numbers, through like repetition, basically.
Exactly, yeah. So we went in several studios that has like 15, 17, 20 hertz room modes, and we validated like this. Yeah.
Impressive. Yeah, because that's really that's like the hardest thing to do. Down there, everything, all bets are off. Most rooms aren't even properly isolated down to 15 hertz. So your standard anechoic chamber, I think they do, what is the standard is like 63 hertz bottom end for standardized testing, right?
Yeah, exactly.
Because one reason is that they can't isolate the room properly below that, and you have potential street noise, I don't know, large water like drainage running below the building that can introduce noise at those low frequencies. So it's ridiculously hard to get accurate data down there.
Exactly. So, and as you said, this is really difficult to find a room, and then you find it. And as I said, you go one day and it works, the other day it doesn't. So you just went to the studio for nothing, and you just go back and forth.
And you don't even know why, maybe, right?
That's right.
Oh, man. Incredible. Yeah, what a pain, but worth it, because again, it's the outcome is absolutely unique and yeah, very impressive. How much does the experience developing speakers impact developing, or did it impact developing this technology? Like, because they seem quite different, the way you talk about it. Obviously, many of the tools will be similar, but the way you use the transducer is completely different. So can you talk a bit about like the kind of the similarities or non-similarities between speaker design and active bass trap design, let's say?
Yeah. What I would say is that at PSI, we master DSPL and the phase since a long time.
Yeah.
And the secret behind the absorber is really the phase mastering. So you have to play a lot with the phase to understand what's happening in the absorption world. And what helps us a lot is that we know how to handle the phase. At the beginning, it was in an analog way with the all-pass filters and everything. So it really helps us to develop the C20. But in the end, it's really how you master the transfer function between the microphone and the transducer. And we are doing it between the XLR of the monitors and the speakers, but we are doing it between the microphone and the speaker as well. So it's not similar in the way you develop it. It's really similar in the way you master the transfer function between.
Interesting. Okay. One of the things that I've experienced, and this definitely plays into what you were saying about it's randomly not working when you're experimenting. In many cases, I ended up just placing it like behind a couch, which from the I guess the theory shouldn't really be ideal, right?
That's right.
But then you place it in an awkward place where it's not supposed to go, and it worked perfectly. Yeah, that's what do you have to say about that?
Yeah. So as you said, it's really difficult to understand the room acoustics, really in the small rooms. It's like crazy because if you have a perfect cubic room, then it's quite obvious the corners are more or less 90% of the time, that's the right place. But then you are placing windows, couch, or I don't know what, and the acoustics change. And then where you think you have the most pressure, it's not the place. So if you don't have pressure, you don't have absorption. You have to measure pressure to be able to absorb. So if you find the right place with the most pressure inside, then you have to place the AVAA there.
Okay, but so that correlation between measuring pressure with Room EQ Wizard and your standard omnidirectional measurement microphone, that is the same way that the microphone in the unit works. So it is a safe procedure to try and identify zones of high pressure for particular frequencies that you're interested in, and then placing the unit there.
Exactly. So for now, we use REW to make it exactly the same. Sorry. So this is the easiest way that we found to explain to people how to place and how to see if it works.
Okay. Because during the setup process, I followed a very simple procedure of just identifying the room modes, figuring out which ones I'd like to attack with the units, and then of the available potential spots where I can place the units, I'd then just measure which one of those has the highest pressure for the particular standing wave that I'm trying to attack. But I didn't make it more complicated than that. So like, I didn't try rotating the units. I didn't try kind of moving it by 30 centimeters here or there. I was fairly straightforward and just going, okay, pressure maximum there at that frequency. That's the one I want to hit. Put the unit there, done. And it worked remarkably well. Yeah. So can you say anything about how much smaller changes, like rotating the units, moving it maybe 30 centimeters here or there, where you're still in the zone of maximum pressure, but you're starting to move out of it, how much does that actually impact the effectiveness? Can you say?
Yeah. So basically, in the low frequency, you can assume that 10 centimeters away won't change anything because you are like in the sine wave, or if we do a bit of theory of the room modes, you are in a sine wave or cosine wave. So at the beginning, it's really the same effect. You have the same pressure in the whole corner.
Yeah.
But then rotating and moving a bit the unit is more for the higher frequencies. So if you have an object not that far, or a reflecting surface, or whatever, I don't know, then you are impacting the more higher frequencies, because in the AVAA, we don't have like a low pass filter at 150 that cuts everything. We have to avoid having the feedback effect. We cannot cut like crazy, so we have to let a bit roll off the high frequency. So it's better to play around with the rotation of the unit and the object near or close to it, just because of the higher frequencies.
Got it. Okay. Interesting. You were talking about the feedback, and to me, that was one of the funniest thing about the unit, that it likes to sing. That's how I describe it.
Sometimes, yeah.
Sometimes it likes to sing, and I couldn't quite figure out exactly when. Like sometimes I noticed that it goes into its own resonance when I get close to it, just moving past it. My body obviously triggers something. But can you give us like an overview of what is happening when this thing goes into resonance?
So basically, everyone knows the feedback effect, because as soon as you place a microphone in front of the speaker, then the problem comes. But so in the unit, it's exactly the same. So you have also to master how to cut off the high frequencies to avoid, as its maximum, this kind of effects. But for sure, the high frequencies are still in the object. And if you have a room or an object that increase the gain in the high frequencies, and unfortunately you have the 180-degree phase shift at this frequency, then as soon as you go too close from the device, you increase a bit more the gain, and it becomes the feedback effect.
Got it. And so it's just feedback. Really?
Yeah,
in a way.
Unfortunately. And so in the C214, we put a lot of effort to do this anti-feedback, which means it starts to sing and then you cut the gain. So we detect the instability and we try to lower the gain to avoid this kind of effect. But you can not really detect it before it starts.
Okay, got it. Yeah, yeah, because it doesn't continue singing. It's not uncontrolled resonance. It very quickly stops, and
Exactly.
it doesn't seem like there's any danger to the unit when it happens. It's like the protection circuit works, but okay, interesting. So the buttons for controlling the gain, they just control the gain of the microphone, or is there
Exactly.
something more complicated going on there?
So for now, it's only the gain of the microphones, because we were thinking of like modifying the low pass or something more complicated. And the advantage of the AVAA is really that it stays simple in its usage.
Yeah.
So you place it, you start, and normally it works. You just have to adjust a bit the gain. If the buttons start to like have a low pass, have a high pass, you can adjust this and this. So we didn't want to have a too complex product.
Great, amazing. And that really leads me to kind of my final question as we're about to wrap this up, which is, if you could talk about it, what does the 5th generation look like? What does the 10th generation look like? What else could be done with this?
So yeah, maybe 2nd generation product would be a bigger one. So not lower in frequency, but higher in SPL, because now we are reaching 115, 120 dB SPL in the corners. And as you know, you reach it very quickly in the low ends.
And just so I understand correctly, that just basically means that it's better at absorbing sound for the same size. Is that correct? Or what does the added gain actually give us?
So basically, if you want to handle 135 dB in the corners, you have to have a microphone which can handle it.
Ah, that way around. So if the sound wave has a higher SPL, let's say 130 dB, does that mean the microphone at the moment is clipping and therefore does it stop working completely? But because that wasn't my impression.
No, so it's not stopping working, but it's at 120, it's clipping, so it's doing its maximum, but you cannot reach the end of the shape. But as the sound decreases quite quickly at the beginning of the signal, then the C214 is able to make the course or make his delay in a few oscillations. But the product would be more for home cinemas, clubs, and maybe big studios where you have a lot of bass in the low end. And 130 is really quickly achieved in the corners. Yeah, sorry. So the idea is to have a microphone that can handle 130, and you have to increase the size of the transducer to be able to absorb as well. But it means not especially a bigger size of the object, but really that you can have more SPL in the corners.
Okay. Roughly speaking, how big is the transducer now?
It's 2 times 14 centimeters for now in the C214.
So it's one at the top and one at the bottom, and then the microphone.
Yeah, exactly.
In the middle. Okay.
So microphone is just above the second one. So it's not in the middle. So if you turn it upside down, you have chances to maybe make something better in the absorption.
Okay.
That's what one of my tricks is. Sometimes you turn it upside down and sometimes it starts to absorb. Don't know why, but that's the game.
And so again, just kind of pushing on this a bit more, wild ideas in terms of the technology or products. I'm sure there are ideas floating around in the company of what you could potentially do with this. Is there anything you can share, you're allowed to share, or that is just maybe just some fun ideas that are never going to happen, but that potentially would be possible?
The perfect idea would be to have a room full of transducer and microphone and like master perfectly the absorption.
Maybe also finally getting an anechoic chamber that doesn't require 2-meter foam spikes and still only works down to 63 hertz.
Exactly.
That could be interesting.
So you could imagine having an anechoic chamber with like a kitchen, or you could have a kitchen with an echo chamber, which is less difficult, I would say. Yeah. But yeah, exactly. That's mastering the room acoustics with the absorption.
Well, it makes us dream, right?
Yeah, exactly. That's really a dream, but who knows?
Who knows? Yvan, maybe let's wrap it up there. Thanks so much again for taking the time. Again, I can only say hats off. I think
Thank you very much.
PSI has achieved the goal of being the creators of the active bass trap. And again, in particular, also to you for taking the time, explaining it to us, and all the best.
Thank you for letting me explain and for taking the time as well. Thanks to you. See you soon. Bye-bye.